Let us solve a numerical example including a dielectric. So let us take a spherical shell which is made of a dielectric. So this is a spherical shell with the inner radius Ri, outer radius Ro, and this is a dielectric. In one of our previous example it was conductor, now it is a dielectric. Now we are given that there is this point charge q at the center of this dielectric. Now what we want to do, we want to calculate E, D, V and P, the electric field intensity, the flux density, the potential and the polarization vector at various parts. So let us see how to calculate. So as we have seen that D is equal to epsilon naught E plus P, or I can write P is equal to D minus epsilon naught E, or I can write it as epsilon naught epsilon R E minus epsilon naught E, or I can write it as epsilon naught epsilon R minus 1 E. So this is the equation which we utilize in solving or finding the polarization vector. So now let's start. It is given that this is epsilon R, the dielectric constant is epsilon R. So let us solve for the case when we are seeing in the region outside the spherical shell. So let us take a Gaussian surface. This is the Gaussian surface with radius R. It is also again spherically symmetrical Gaussian surface, although the drawing does not show because I'm not able to make a proper circle or sphere here. So this is spherical Gaussian surface with radius R in a case that R is greater than R naught. So let us try to find this electric field in this region. So using Gauss law, ER1 into 4 pi R squared, since this spherical symmetry dictates that the field should be in radial direction, so I am directly solving the integral and it comes out to be ER1 4 pi R square, and it should give you the total charge enclosed. Now in this dielectric it is electrically neutral, so total charge is 0, only this point charge is the charge enclosed divided by epsilon naught. So the electric field in this region is q by 4 pi epsilon naught R square. So the potential in this region is simply q by 4 pi epsilon naught R, which we can easily calculate from E dot dl from infinity to point R minus sign. So this is simply, we can easily find out the potential, which comes out to be this. Now in this region the medium is air only, so dr1 is simply epsilon naught er1, and it comes out to be from this equation q by 4 by epsilon naught, epsilon naught will be cancelled out by multiplication, and direction is the radial direction. So for this region we have found all these three equations, and P will be simply epsilon naught epsilon R minus 1 E. Epsilon 1 R is 0, 1 for the air, so this goes to 0. So 1 minus 1 is equal to 0, so this is 0. So polarization vector in air is simply 0, means there is no polarization. Now let us try to solve for a case when we are inside the dielectric shell or the meat of the dielectric. So let us take the case when we are inside the dielectric shell. So this is the dielectric shell. Let us make a Gaussian surface. This Gaussian surface which I am making is inside the shell. It is spherically symmetrical. So this is Ri, this is Gaussian surface R, This is Gaussian surface, and this is external surface of the shell or not. Now again, this symmetry dictates that the field should be radial. So ER2 4 pi r square is equal to the total charge enclosed q by 4 pi q by epsilon not epsilon r. So we will find that ER2 is simply q by 4 pi epsilon naught epsilon r square, and the direction is the radial direction. And the flux density in this region is simply epsilon naught epsilon r ER2, and it comes out to be q by 4 pi r square AR. Now you might wonder how I directly wrote this ER2. No need to worry, you can use this form of Gauss law, where we will just bother about the free charge density. So we know that D dot ds will give you the only free charge, and the free charge is simply this q. So this is just this q. So we know due to symmetry d will be radial, so it is d 4 pi r square is equal to q. So d is simply q by 4 pi r square, and from this we can find e is simply d by epsilon naught epsilon r. So e is equal to q by 4 pi epsilon naught epsilon r square AR. So we could have gone this way, but since I already knew due to symmetry all those things, so I did not did not go through this way. Now we need to calculate the polarization vector. Polarization vector was, as we saw in the previous slide, was simply epsilon naught epsilon r minus 1 e. So let us put the value epsilon naught epsilon r minus 1, and e is q by 4 pi r squared. So if I take epsilon r common, I will have 1 minus epsilon 1 by epsilon r q by 4 pi r square. So this is the polarization vector, and its direction will be radial only. And I can write this epsilon naught epsilon r as simply epsilon. So this comes out to epsilon 1 minus epsilon r q by 4 pi r square AR. Now let us try to calculate the potential. Now the potential in this area, or at our Gaussian surface, is simply, let us say, V2 is equal to minus infinity to, first we will reach to RO, ER1 dot dr minus from RO to R ER2 dot dr. So V2 will be, this will give you q by 4 by epsilon naught r naught, and this will give you q by 4 pi epsilon, where epsilon is epsilon naught epsilon r. This is epsilon 1 by r minus 1 by r naught. So V2 will be q by 4 pi epsilon naught, I will take the common, 1 by r naught plus, I will write it as epsilon naught epsilon r only, 1 by epsilon r into 1 by r minus 1 by epsilon r into r naught, or I can write it further as q by 4 by epsilon naught into 1 by r naught. I will take common 1 minus 1 by epsilon r plus 1 by epsilon r into r. So this is the potential at the Gaussian surface inside the dielectric. Now let us try to find the three parameters inside the cavity of this dielectric shell. So again I have made this shell. This is the charge. Now we want to find inside this thing. So let us say this is the Gaussian surface with radius r. This is this is ri inside radius, and this is ro. So again d dot ds should give you the free charge enclosed, which is q. So d into 4 pi r square will give you q. D is equal to q by 4 pi r square. Now the medium is air only, so E is equal to d by epsilon naught. It will give you q by 4 pi epsilon naught r square. So this is dr3 er3, and the direction will be radial due to spherical symmetry. I have found these two. Now I want to find polarization. Polarization will be epsilon naught epsilon r minus 1 E. Now epsilon r for air is 1, so this will give you 0. So polarization is 0 inside. Now we want to find the potential. Potential for this, we will again come from infinity to r naught minus E r1 dot dr minus from r naught to ri er2 dot dr minus er3 dot dr from ri to r. So let's see what we will find. From this first we will find q by 4 by epsilon naught r. From this second we will find q by 4 by epsilon naught epsilon r, 1 by ri minus 1 by r naught. And from this third we will find q by 4 by epsilon naught 1 by r minus 1 by ri. So taking things common and again writing it properly, so what we will get? We will get v3 is equal to q by 4 pi epsilon naught. I will take common 1 by r plus 1 by 1 by epsilon r common 1 by ri minus 1 by r naught plus 1 by r minus 1 by ri. Or further simplifying, v3 will be q by 4 by epsilon naught this will be r naught, so it will be 1 by r naught. I will take common 1 minus 1 by epsilon r plus this is 1 by r minus, take the minus sign common so that it is easier for us, and remaining quantity is ri. So 1 by ri I will take common, so 1 minus 1 by epsilon r. So the potential inside the shell at any point which is at r distance from the center is q by 4 pi epsilon naught 1 by r naught 1 minus 1 by epsilon r minus 1 by ri 1 minus 1 by epsilon r plus 1 by r. So these are the three parameters we wanted to calculate, and we have already found the this thing, the polarization. Now let's try to plot them. So from previous slides we can see that dr1 was equal to q by 4 pi r square, dr2 was again q by 4 pi r square, and dr3 was again q by 4 pi r square. So its value does not change. In all the three it will remain same. But er1 was q by 4 pi epsilon naught r square, er2 was q by 4 pi epsilon naught epsilon r square, and er3 was again q by 4 pi epsilon naught r square. So this value does change, and the polarization vector was 0 here, it was non-zero here, and it was again 0 here. So you see, in this way now we can plot the values. So let us plot the flux density d with respect to r. So it is continuous like this, but for field what happens, it is, let us say, r naught. From r naught to ri, it is going to follow a little different path with 1 by r square thing only, but reduced by a factor 1 by epsilon naught r. So for this portion the field will follow, electric field intensity will follow this curve. So there is this continuity in the electric field intensity. And what about potential? We can easily calculate that potential will be continuous function, but its value will gradually little bit change like this. 1 by, this is r naught, this is ri, oh sorry, this is ri, and this is r naught. Again I am doing the same mistake, this is ri, this is r naught. Okay, so this will be continuous, and again polarization vector, you see it is 0 up to ri, decays from a value to r naught, again it is 0. So this is the polarization vector. So in this way we have plotted all these three values. Now let us try to verify one thing, the surface charge density. Because of this polarization, we know that the surface charge density because of this polarization is given as p dot an. So let us take this shell again. Now I want to find the surface charge density due to polarization at this inner surface of the shell, this inner surface of this shell, how much surface charge density it is going to have. So for this unit vector is in this direction, radial direction, but in this direction. So an will be in minus ar direction, and p will be pr3, which we calculated. So sigma ps is equal to, what was the value of p? The value was 1 minus 1 by epsilon r q by 4 pi ri squared. I think this was the value in direction of ar. Dot minus ar is this thing. So it is going to come out to as 1 minus 1 by epsilon r q by 4 pi Ri square. So this is the surface charge density which is going to appear in the inner side. What is the value which is going to appear on this outer side, this surface of the shell, this outer surface of the shell? For this, the outer radial vector will be like this. So an will be equal to ar. So sigma ps will be p dot ar or pr2 dot ar, and it will come out to be 1 minus 1 by epsilon r q by 4 pi r naught square. So this is the surface charge density. So you see the surface charge densities are little different. This surface charge density is higher because this Ri is small. This surface density is low because this is larger. R naught is greater than Ri. But the total charge is same. Total charge, because of this we can take out as 4 pi Ri square, and this is 4 pi R naught square. You will find that these two charges are equal and opposite. So total charge is again 0. So this is what we can verify, and we can find the volume charge density because of polarization by simply minus del dot P. Now you see it will come out to be minus 1 by R square dou by dou R square into PR2. So putting the value of PR2, which was something proportional to Q by R square into R square. So this will get cancelled out. So there is no function of R here now. It will go to 0. So you see that there will not be any volume charge density because of the polarization inside this dielectric shell. So in this way, we have solved a numerical example which is trying to show how to deal with the dielectrics when it is placed in an external electric field. And in this way, we can use the concepts of dielectric constant, the electric flux density, and the potential to calculate the values. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join us in our Telegram channel for doubt discussion, whose link is given in the description of this video. Thank you.